We're going to start with trigonometry. The best way to describe it is to kind of go back to something that's familiar to you, and that is that let's say we take a line and we just run with it. So we take a line, we talk about money. You work more hours, you get more money if you're working. If you travel in more time, you go a greater distance. Most functions that we're interested in at a kind of a starter level, like a algebra 2 level, is what we call non-bounded. Just keeps going and going and going and going. You save more money, you have more money in the bank, right? But not everything is that way. Some things are what we call bounded, and bounded would mean, sometimes let's say you're going to add some water to a container, and then after a certain point when it's full, you dump it out, okay? And then you fill it up, and then you dump it out. Or tides, or it's hard to talk about anything having to do with tides and not think of those poor people in Florida dealing with all the terrible things going on there. But there's some cyclic activity that goes there. Waves will have crests and troughs. But a lot of times things are bounded. You can't exceed. Think of sunlight. The sunlight on the day, you're going to have a certain amount of time when the sun's out, and then the sun isn't there because of the turning of the earth. So you can plot maximum temperatures. You can top all kinds of different things, the height of the sun in the sky, whatever. But those bounded activities bring us to this, the unit circle. And the idea of the unit circle is that water and sun, outdoor temperatures, lots of things that are bounded. So trigonometry is a bounded set of functions. And what's really cool about it, it's actually one of the best fitting real-life fits of all of the math functions. When we go to the Mall of America in December, those rides that spin around like this, and you look at the far distance, close distance of a ride that comes, it goes in a circle, you're going to be able to make functions that fit really well because of the consistency and accuracy of these formulas. So let's talk about the unit circle a little bit. Unit circle is any radius that you want. But what would be the easiest one? What? 1. Yeah, 1 is the easiest. Because what's anything divided by 1? Itself. So unit circle is a convenience of radius equal to 1. We could use any radius we want. We choose 1 just because it's easy. But you could use any radius that you want. Well, let's talk about, so points on the circle. So if this is 0, 0, the radius of 1, that point out here is going to be 1, 0. This will be negative 1, 0. This will be 0, 1. This will be 0, negative 1. All because of the convenience of radius 1. So when we're looking at distances, you're used to, if this is 5 and this is 4, pretty easy to find this distance. How are we going to do that? Pythagorean theorem. 4 squared plus 5 squared square root. And so you could figure that out. But a lot of times you're not given 2 sides. You might be given a triangle, but you're only given one angle. Like let's say the angle is 30 degrees. And you don't know this side, but you know this side. Well, we can still fill out this using these relationships. And so I'm going to prove this really quick because it's so easy. I wouldn't do it unless it was easy. We're going to have theta. Here's x. Here's y. X is the distance from the origin to where our point is, x comma y. And then what we'll do is we're going to use the SOHCAHTOA, which is a relationship, SOHCAHTOA. What was sine equal to on our triangle? This was opposite, and this was hypotenuse. And what was A again? Adjacent. So if the cosine was adjacent over hypotenuse, and the hypotenuse was a radius of what did we say? Oh, 1. Okay. Cosine would be here, and the 1 would be here. Then where would sine be? Opposite over hypotenuse, and so you'd have that there. So now we have two triangles that have the same angle and the same radius. So therefore, we could say that x is going to be what? Your cosine, because if these are both 1 and these are the same angles, then by triangles being similar, actually they're congruent here, you can say x is the cosine, and then what's y? That's the sine. Let's try it a different way. Let's say we have these two triangles, they're similar triangles. That means that we can say that x over 1 is equal to what over 1 in this triangle? X over 1 is equal to cosine over 1. And y over 1 is going to be equal to sine theta over 1. By the way, we don't say sine, we say sine of theta. It's like saying squared. Doesn't make sense. X squared, y squared, what is it? 4 squared, you want to say the function of that angle. Okay, well there you go. There's these. And oh, we are going to have a bonus here. I like bonus. The tangent of theta is the sine over the cosine. But how did they get that? Well, it is TOA, which is opposite over adjacent. And what is the opposite of this triangle? Sine of theta. And the adjacent is cosine of theta. So there we've got tangent, which is sine y cosine x. Usually we say sine theta over cosine theta. Seem easy? Yay, I like starting out easy. So then what we can do is we can build relationships between all of the points on the unit circle. Well, that would take an infinite amount of time. So let's do fewer ones. Let's do the easy ones. Let's do 0, 30, 60, and 90. And there's another one in here we're going to do, which is going to be 45. Okay, and just by what is in there, see if you can put as many of the values in there as you can. And some of them you'll remember. Go ahead and fill that chart out. Kind of some helpful practice there. Radians, again, everybody knows what a radian is? Anybody doesn't know what a radian is? Let's go real quick what a radians are very helpful because if you go around a circle, how many degrees in half a circle? 180. Why? Why is it 180? Oh, it's half of 360. Good. Why is a full one 360? You're close. The Greeks made it up. They love the number 60. 60 is a number that's divisible by 2. What's divisible by 2? 60 divided by 2 is 30. What's 60 divided by 3? 60 divided by 4. 60 divided by 5. 60 divided by 6. They loved 60. It was divisible by 1, 2, 3, 4, 5, 6. They loved it so much that they just made it up. Okay, 6 is a real divisible number. 1, 2, and 3. Why not take 360 as 60 times 6? And it's very, very divisible. So that's what they did. They made it up. If you go to another universe, and I know some of you will, that is going to, they're not going to have 360 degrees. But what they will have is the number of radii that are stuck on a circle on the outside. And do you know how many radii it takes to go halfway around a circle? A little bit more than 3. And so 0.14159 radii plus 3 gives me pi. And how many to go all the way around the circle? 2. Or tau is the constant for, I guess, diameters going around the circle. So what's neat about this is you could go to anywhere in the universe, and I just heard the Voyager satellite is just leaving the solar system. It's going out. It's a man-made satellite that they still are getting data from, going out past the solar system. If they go to another planet system, they're going to find that they're probably somehow using mathematically for angles, they're probably using radians. And what's the base word in a radians? Radius. So it's the number of radius on the circle. So when we say 30 degrees is pi over 6, we're saying there's pi radians, and if you divide it by 6, 1, 2, 3, 4, 5, 6, you're going to get 30 degrees. Well, the easy way that I like to do it is 180 degrees in pi radians. And then whatever you want to do to convert that, if I want degrees, so I take 30 degrees, I want the degrees to cancel out. So do I put 180 in the top or 180 in the bottom? In the bottom, so therefore you can go pi over 180 or 180 over pi. In this case, you can see real quickly that this is going to be pi over 6. And you can do that with any of those conversions. This will be pi over what? 4. Pi over 3. Now it's getting trickier. How many pi over 4 is this one? 3 pi. 150 is right here. How many pi over 6 is that? 5. 240 is down here. How many pi over 3s is that? 4 pi over 3. Or let's see, 1, it'd be 1, 2, 3, 4 pi over 3. Yep. And then 315 is right here. How many pi over 4s is that? 7 pi over 4. Good. And then all you have to do is pick on what the y value is for the sine. And let's just do this real quick. What's the y value for 30 degrees? Square root of 3 over 2 or 1/2? 1/2. What is it for pi over 4? Can't get that one wrong, can you? Because they're both square root of 2 over 2. 60, what is it going to be, the y value? Square root of 3 over 2. 135 is in the middle here. That's going to be square root of 2 over 2. That's not negative, though, because we're going up for y. 150, we're still going up 1/2. 240, we're going down, square root of 3 over 2. 315 is going to be down, square root of 2 over 2. For cosine, it's how far we're going over. And I'm not going to do all of these, but I'm going to do a couple of them. How far over x are we going for 30 degrees? Square root of 3 over 2. And then the next one is the same, square root of 2 over 2, and the next one's going to be 1/2, because we're only going over 1/2. For tangent, all you do is take sine over cosine. So you just divide these out, and you're going to get 1 over square root of 3, because the 1/2s are going to cancel. What's square root of 2 over 2 over square root of 2 over 2? 1. And then here the halves will cancel, and you'll just get the square root of 3. These three I'm going to want you to know, because we're going to use those a lot with complex. And then you could finish that off. But is it coming back to you a little bit? All right. One last thing that I want to do before I turn you loose on some problems, and that is, let's say we give you a point, and then I give you some directions on where to move the point from that spot. Now, we can use some various formulas for this, or we can use some brains. What you want, brains or formula? Brains? Okay, let's do brains. So let's say I take 30 degrees, and you said that was the square root of 3 over 2, 1/2. Everybody find this one? Show me that you have this slide, because I want everybody to understand this one totally. Okay, so which is the sign, the x or the y? Which is it? It's the y. So the sine of theta is just 1/2, so no big deal. What is this second one telling us to do here if it's the sine of theta plus pi? We're here, we're going up theta. Now we're going how far? Where are we going on the circle? We're going additional pi, right? So that is straight across the circle down to here. Now, can you look at this point and tell me what this point is going to be? Well, it'll be negative x. I agree with that, because instead of going forward x, we're going backward x, right? And then instead of going up y, we're going down y. So therefore, this will be negative 1/2. So what's the sign of this going to be, the x or the y? The y, so it's negative 1/2. What if we did the sine of theta minus pi? So instead of going this direction, we go in the opposite direction. Do we end up at the same point? So do we have the same answer? Yeah. Negative 1/2. Now this is where it gets good, I think. Now what we're saying is pi minus theta. So what they're saying is go to pi first, and then back off theta. What will this point be? It'll have a square root of 3 over 2 and a 1/2 in it, but what's going to be, negative? We're going, instead of positive x, we're going back x, right? So this will be negative, but we're still going up y, so that's still positive. So what's the sign of this one going to be? 1/2, yep. All right. Here's an easy one. We start out at theta, and then we're going to add 2 pi to it. Well, what happens to that? It's the same point, so that's just going to be 1/2. So all these are either 1/2 or negative 1/2, and now we're ready for the final one. It says go to pi over 2. So we're going to go up here, and then we're going to back off 30. This is 30, or theta. Okay? What's going to happen to this point if this is 30 and this one is essentially 60? Yeah, they switch, don't they? Yep. And so what happens is the sign for this one's going to be the square root of 3 over 2. And this is what we call the complementary formula. And we'll talk more about the complementary formula a little bit later. If you are making sense of this, just do this one real quick. So complementary in geometry means adds up to 8, it adds up to 90. And so what do you notice about 30 and 60? They add up to 90. So the sine of 30 is equal to the complementary sign of 60. What's quicker than complementary sign? I don't want to write out complementary sign. What's quicker? Cosine. Co. Do you know that? Cosine is the complementary sign. They add up to 90. So this identity, which we're going to look at a lot, that identity just comes from complementary sign. All right, and then for homework, you're going to fill out a couple of charts. And then I just wanted to real quickly show you, without using a calculator, the sine. Find the sine if the cosine is 2/3. Let's say the radius is not going to be 1. We can still work with it. Right triangle between 0 and pi over 2. The complementary sign is 2/3 adjacent over hypotenuse. What will this side be? Very good. Square root of 5. In quadrant 1, is it positive? Yes. So what's the sign of this going to be? Just looking at it quick. Square root of 5 over? Done. Easy.